A horizontal wire AB of length L and mass M carries a steady current I1 free to move in a vertical plane is in equilibrium at height h over another parallel long wire CD carrying a steady current I2 which is fixed in a horizontal plane as shown. Derive the expression for the force acting per unit length on the wire AB and write the condition for which wire AB is in equilibrium. So we are asked to find or determine, okay? So I'm writing in this way. To determine one, force per unit length, okay? So this is force per unit length. This is force per unit length on the wire AB. Next, okay, we have to find condition for which wire AB is in equilibrium. So we have to determine, okay, this, okay, force per unit length on the wire AB, and next condition for which wire AB is in equilibrium. Now we have wire AB which can move freely in a vertical plane, okay? So from question, wire AB is free to move in a vertical plane. So we have this, okay? Wire AB is free to move and wire CD is fixed, okay? And I1 is the steady current flowing from end A to B in wire AB, and I2 is the steady current flowing from end D to C in wire CD, and wire AB and CD are separated by distance h. Now, what we find from this diagram is that, okay, so I'm writing wire AB is above, okay, the wire CD. So we can say this, okay, from the diagram or figure given in the question, okay. So we have this. Now, what we find is that, okay, wire CD, okay, carrying current I2 produces magnetic field, okay, it produces magnetic field, okay. So we need to find the magnetic field, okay. So I'm writing in this way, okay, this is in magnitude, this is what, this is magnetic field due to wire CD carrying current I2. So we have this. Now, the magnetic field in this region, okay, in the upper region. So this is the upper region, okay. So what we find, wire AB is in the upper region of wire CD or is above wire CD. So magnetic field in this region, okay, we need to find this, okay. So as we know, wire AB is at height h above the wire CD. So let me write in this way, okay? Magnetic field due to wire CD. So, or let me write over here, okay? Magnetic field due to wire CD carrying current I2 at height or distance h. So this is mu naught I2 by twice pi h. So we have this. This is magnetic field due to straight conductor, okay? So we know magnetic field due to long straight conductor. So this is what we are using the concept of, okay? Let me write over here. We are using the concept, okay, of magnetic field due to long straight conductor, okay? So we are using this concept, long straight conductor carrying current at distance h, okay? So we are using this concept. This is the concept. Now, so let me write over here. BCD is the magnetic field, okay? So I'm writing in vector form, okay? This is magnetic field due to wire CD, okay, above it at height h from it. Now we need to find the direction, okay? So what we do in order to find the direction, okay? So I'm writing over here to find the direction of magnetic field due to wire CD. We use right hand rule, or simply we can tell, okay, we use right hand thumb rule. So what you find, okay, current is flowing from D to C. So let's say this is D, okay, and this is C. The sharp end is C. So current is flowing from D to C. That is, it is flowing along this direction. So when I hold conductor CD in my right hand, okay, when I hold it in my right hand with thumb pointing in the direction, okay, of current, then the crawl of the finger, okay, crawl of the finger in the upper side or upper region of wire CD is what? It is in inward direction. So what you find? Magnetic field in the upper region of wire CD, okay, so is perpendicular to the plane of the board and is acting in inward direction. So we have this, okay. So this magnetic field, okay, is perpendicular to the plane of the board and is acting in inward direction. So what we find? Is perpendicular to the plane of the board and is directed, okay, and is directed inward. So we have this. Now what we find is that, okay, in the presence of magnetic field BCD due to conductor CD, okay, or wire CD, we can write conductor or wire CD. The wire or conductor AB carrying current I1 experiences force. So we have this, okay, in the presence of magnetic field due to current carrying conductor or wire CD, okay, the wire or conductor AB carrying current I1 experiences force. So let F AB, okay, this is force. So I'm writing in magnitude, okay, this is force experience by wire or conductor AB carrying current I1 in the presence of magnetic field BCD produced by conductor or wire CD. So we have this. Okay, so I'm writing in magnitude, or we can write in this way also, okay, in vector form. Now we need to find this force, okay, in magnitude as well as in direction. So I'm redrawing the figure, okay. So we have this diagram. Now what we find, as I said earlier, we need to find this, okay, force experienced by AB. So force experienced by current carrying conductor in the presence of magnetic field, okay. So I'm writing over here. This is force experience, okay. So let me write over here. This is force experienced by current carrying conductor, okay, in the presence of magnetic field, and the force is given by current element cross magnetic field. So we have this. So we are going to use this concept, okay. So we have current I1 flowing in conductor or wire AB. So we can write in this way, I1 L, okay. So this is current element, okay, cross magnetic field. So we know magnetic field is BCD, okay. So we have magnetic field BCD, okay. So magnetic field is BCD. So we have this, okay. So I'm writing in vector form, okay. So now what we do, let us write in magnitude, okay? This is I1L BCD, okay, sine theta. Now what we find? Angle between, so current element and magnetic field, okay, we need to find that. So for that, let us take a small, okay, small elementary length, okay, of wire AB. So this is called current element. So we find current element is horizontal, okay, and we find magnetic field acting in inward direction. So we have this. Clear? Or we can understand in this way also, okay, graphically. Let us take this as X, okay, and let us take this as Y, and let us take this as Z. So we find magnetic field acting along Z axis and current element is along X axis. So angle between current element and magnetic field is, okay, 90 degree. So let me erase this first, okay. So angle theta equals 90 degree, okay. So therefore we can write FAB equals I1L BCD, and we know theta is 90. So this gives me 1. Therefore we can write force experienced by conductor AB equals I1L BCD. And what is the value of BCD? Okay, we know magnetic field due to conductor CD is mu naught I2 by twice pi H. Okay, so we are going to put magnetic field due to wire CD. So we can write in this way, okay, I1L. So this is BCD is mu naught H by, mu naught I2 by twice pi H. Okay, so we have this. Let us see. Mu naught I2 by twice pi H. So we have this. Therefore, I'm writing in this way, okay. FAB equals mu naught I1 I2 by twice pi H, and we have L, that is length, okay, of wire AB. Now we are asked to find force per unit length, okay. So I'm writing in this way, FAB by L, okay. So this equals mu naught I1 I2 by twice pi H. So this is, okay, this is force per unit length on wire AB. Okay. Now, next, we are asked to find the condition for which wire AB is in equilibrium. Since wire AB is free to move in a vertical plane, okay, we are asked to find the condition at which wire AB is in equilibrium. Now, let us find the direction of this force, okay? Because we are going to find the condition for equilibrium. So the force or all the forces acting on the wire AB must be balanced. So let us find the direction of this force. And in order to find the direction of the force, okay, we use Fleming's left hand rule. So what we find in wire AB, okay, we find current flowing along this direction from A to B, okay, and we find wire AB is in the presence of magnetic field acting perpendicular to the plane of the board directed inward. So we use Fleming's left hand rule, okay. So to find the direction, so let me write in this way, okay. So to find the direction, we use Fleming's left hand rule. So this is my left hand, okay. Now I'm pointing my first finger in the direction of magnetic field BCD. And as we know, BCD is perpendicular to the plane of the paper and is directed inward. So thumb is pointing along the direction of magnetic field, okay. It is pointing inward to the plane of the board, okay. And my central finger, okay, this finger, central finger, gives the direction of current. Here, this gives the direction of current, and the thumb, stretch thumb, gives the direction of force. So that force on wire AB, okay. So I'm drawing over here. Force on wire AB acts in upward direction. So this force, okay, this force is directed upward. So using Fleming left hand rule, force on wire AB, okay, is in vertically upward direction. So we have this. So I'm drawing conductor AB, okay. Current I1 is flowing along this direction, and force on AB act in vertically upward direction. Okay, it is act in vertically upward direction. Upward direction. Now, we are asked to find the condition. Okay, we are asked to find the condition for which wire AB is in equilibrium. So, to be in equilibrium, okay, this force must be balanced by the weight. Okay, must be balanced by the weight of wire AB. So, we have this, okay. Let's see. We are asked to find condition for which the wire AB is in equilibrium. So we have this, okay. Clear? So I'm writing over here. To be in equilibrium, okay. We write in this way. Weight of wire AB per unit length, because we have force per unit length, okay. We have determined force per unit length. Clear? So this must be equal to force on wire AB per unit length. So we have this. So to be in equilibrium, we must have weight of wire AB per unit length equal to force on wire AB per unit length. So we can write in this way: weight of wire AB per unit length must be equal to force on wire AB per unit length. And we know force on wire AB per unit length equals mu naught I1 I2 by twice pi h. So we can write in this way, okay? Weight of wire AB per unit length must be equal to mu naught I1 I2 by twice pi h for wire AB to be in equilibrium.